Hello, hello. So we've been doing vectors in a plane, vectors in a 2D plane. Now we're going to do vectors in space. So let's go. We are going to go from 2D to 3D. The whole point of multivariate calculus is to take you from this kind of math to this kind of math. And that starts today. So first we're going to talk about coordinates in space. And I can't scroll on my screen. There it goes. Coordinates in space. So if you want to plot a point in space, it's very similar to plotting points in a plane, but instead of going like over and up, you kind of have to go over one way, over another one way, and up a little bit. So I will show you. So these are pictures of what the 3D plane looks like. So we have X coming out right here. This is the positive X-axis. This is the negative X-axis, the positive Y-axis, the negative Y-axis, the positive z-axis, and the negative z-axis. So you have 3 axes, which actually creates 8 regions called octants. And you don't even need to know how to number them, except that this one right here, where everybody's positive, this kind of front one, that's octant 1. So if I ever say you're in the first octant, that means everybody's positive or 0. So over here, we have a picture of a point that's been plotted. This is the point XYZ. I'm going to move my face up here because my hand keeps hitting it. So that thing right there is the point XYZ. And the way we got to it was we went along the x-axis X, along the y-axis Y, and then up Z. So let me show you how that works down here. So if I come down here, if I want to plot the point 3, 2, 4, I go 3 out from the origin, and then I have to go 2 out on y. But notice, I don't say here's 3, blah, 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 2 is right there. It's not. I have to go 2 units in the y direction from where I'm currently at pictorially. So 2 units in the y direction is about this wide. So that's this distance. So it almost looks like you're plotting the point 3, 1, but really this point right here is the point 3, 2, 0. 3 on X, 2 on Y. I haven't moved up at all, so Z is 0. And this wants me to go up 4 units total. So 4 units up looks like this, and then you just copy it down there. And this is the point 3, 2, 4. So the tough part is when we're drawing in 3D on a 2D plane on your paper, it's going to look a little funky. You should still understand how it works. I'm going to have you plot some points, but you're not going to have to do this often. I just wanted you to be familiar with it. So if I wanted to use this diagram to plot the point 4, 5, 1, 4 is down here. 5 is over here. So 5 is technically as much as, let's see, 1, 2, I can't even count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes over. So if I start 5 right here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this right here would be, oops, I went the wrong way. Dang it. I meant to do 4, 5, 1. So if 4 is right there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10. So this point that I have right now is 4, 5, 0, and I want 4, 5, 1, so 1 means go up 2 boxes. So that is the point 4, 5, 1, which again looks super weird, but you can make it clearer by drawing in the box that you technically created. Now, I know that gets kind of obnoxious, but you can do that to make it a little bit more clear. I don't care that much. I just want you to understand how it works. Now, if you want the distance formula between 2 points in space, it's really just an extended Pythagorean theorem. Instead of x2 minus x1 squared plus y2 minus y1 squared, you also have plus z2 minus z1 squared, and then you square root the whole thing. So if I want to find the distance between 3, 2, 4, and 4, 5, 1, I'm just going to follow this rule. And who likes writing long things? I don't like writing long things. So this is really delta x squared plus delta y squared plus delta z squared. And so if I go from 3 to 4, delta x was 1. From 2 to 5, delta y is 3. Whoop, not cubed, squared. And then from 4 to 1 is technically -3, but I'm going to square it, so I'm going to just call it +3. So 9 plus 9 plus 1 is the square root of 19. I mean, that's it. And you may be thinking, I wonder why it was that easy. I'll tell you why it was that easy. So let's come over here for a second, and I'm going to draw the best I can a box. So this right here is a rectangular prism, okay? And let's say I want to figure out how far it is from this corner to that corner. Well, if I wanted to figure out how long this red line is, that red line is really the hypotenuse of this red triangle. And the base of that red triangle is really the hypotenuse of this green triangle. So let's say that this right here is the origin. That means that this would be an x distance right here, which is also over there. And this would be a y distance, which is also over here. And if this is a rectangular prism, that's a right angle. And so this hypotenuse would be the square root of x squared plus y squared. So then this is a z distance, making this hypotenuse the square root of z squared plus x squared plus y squared, which gets me z squared plus x squared plus y squared. Ta-da! That's why it's an extended Pythagorean theorem. So if we want to find the distance here, I'm just going to do it one more time. Distance between the points is delta x squared, delta y squared, delta z squared. And so that's 64, 68, 72. And I'm not even going to simplify it because that's how I roll today. All right, so you figured out points in space. We have distances between points in space. Here's the cool thing. Vectors in space act just like vectors on a plane, okay? Most of the rules stay exactly the same. So vectors in space have 3 components, A, B, and C, or V1, V2, V3, doesn't matter. Your first component is your delta x, your second component is your delta y, and your third component is your delta z. The length or magnitude of a vector in space is the same as the magnitude in 2D. You just take the sum of the squares of the components and then square root it. So the square root of a squared plus b squared equals c squared. If you want to write a vector instead of in component form in standard unit vector form, which was ij before, ij now has a k. And so if you want to write it, you could write 2i minus 3j plus 5k, and the k doesn't have a dot, so we just give it a hat. Okay. Add, subtract, multiply by a scalar, creating a unit vector, all those operations remain the same. You just have to do it 3 times instead of 2. So if 2 points have coordinates of 3, -1, -10, and 7, 6, 2, write A, B, and BA in component form, write A, B, and BA in standard unit vector form. If you want to try this example on your own, feel free to pause this, scrub forward, and see if you did it right. I'm going to go through and do it right now. For those of you that just want to see me do it, I can understand that too. So if I wanted to write AB is going to be delta x, delta y, delta z, making BA the negation of that, -4, -7, +12. That's component form. Now, standard unit vector form means that this would be 4i plus 7j minus 12k, or -4i minus 7j plus 12k. BC is 215. Find the coordinates of C. That means to get from B to C, x increases by 2, y increases by 1, z increases by 5. So since B starts at 7, 6, 2, C is going to be at 9, 7, 7. Oops, not a bracket, parenthesis. Find the magnitude of AB and BC, no problem. The magnitude of AB is the square root of the sum of the squares of the components, which are 4, 7, and 12. And let's see, that's going to be 144 plus 16 is 160, plus 49 is 209. And then BC, which they gave us above, is 215. 215 is the square root of 30. Ta-da. All right. 2 more points. Try those. You don't need me. I'm going to even pause this right now and then just make it appear out of thin air. Let's do it. Where's the pause button? It's right here. So hopefully this is recording again. And the answers are right here. One of the things that I wish this said, I'm going to go back and do right now in another color, is I asked for PQ and QP in component form. So I'm going to write PQ in component form, but I'm going to write QP in standard unit vector form. So that would be negative 12i, 0j. So you know what? If I have 0 j's, I'm not going to write j. And then plus 13k, which is a good illustration of when you see things in standard unit vector form, don't assume that it's just always x, y, z, because if one of the letters is missing, that means one of the components was 0. All right. And now, last but not least, we're going to talk about parallel vectors. So parallel vectors are vectors that point in the same direction. That's it. So 2 vectors in space are parallel if the components of one are constant multiple of the components of another. In other words, v and w are parallel if v equals some constant times w. So 2, 3, 7, 12, 18, 42. Are they parallel? Well, x, the x component, got multiplied by 6. The y component got multiplied by 6. The z component got multiplied by 6. Yes, yes, they are. V is parallel to w because w equals 6v. Vectors v, 2, 3, 7, and z are parallel. Solve for k. Okay, so if these are parallel, there's got to be a constant multiple. 2 became negative 4, so I'm realizing I multiplied by negative 2. Therefore, 7 needs to get multiplied by negative 2. Then, why do I care so much about parallelism? It's if vectors are parallel, then points can be collinear. So if the vectors connecting 3 points are parallel, then the 3 points are collinear. Given A, B, and C, show that they are collinear by showing that AB is parallel to BC. So parallel means they point in the same direction. And in this case, I want A to B to look like this, and then B to C to go in the same direction, but maybe be longer, maybe be the same size, maybe be shorter, doesn't matter. But if those 2 vectors that connect A to B and then B to C are parallel, then you've got collinear points. So AB, the vector, is 2, negative 5, negative 8. And BC, the vector, is negative 4, 10, 16. And it sure looks like BC is equal to negative 2 times AB. Therefore, AB is parallel to BC, and ABC are collinear. And that's it. That's all I got. We're done. So I hope you enjoyed this video. I said I'd find a joke, and I didn't even think about a joke. What's a joke I haven't told you guys before? I think I've told it before, but I'm going to tell it again. What did the custodian say when he jumped out of the closet? Supplies! I know. They're so bad lately.